Hey, good morning, everybody. You guys are doing well. I've got coming up on 12 o'clock. I'm gonna give it a couple more minutes. We still got people coming in, so we give it a couple more minutes. Let everybody get caught up here. Hope everybody's doing well. Yeah, just at the 12 o'clock hour, or like 12 o'clock Eastern, we're gonna like some give it. Still got people coming in. We'll give another minute or two here. Happy Thursday to everybody. Excuse me. Welcome everybody that's joining us. We got about 12:01. We still got people coming in, so I'm gonna give it about one more minute, and then we will get going. About 20 more seconds here. We'll get started. Still got people coming in. All right, I guess we'll go ahead and get going. Good morning, or I guess good afternoon to everybody out on the East Coast. Hope you're doing well. Appreciate everybody taking some time out of your day to join us. It was our next installment of our monthly webinar series. Today we're doing Fiber Optics 101. My name is Tim Buffkin. I'm the National Sales Manager of Broadband here at InCab America. So again, yeah, appreciate everybody taking some time out of your day to join us, especially those of you on the East Coast. I know it's your lunch hour, so thanks for joining in with us today. Before we get started, let everybody know this webinar is RCEP compliant. So basically means that we met the standards and requirements of the registered continuing education program. You can earn continuing education credit hours at the end of this webinar. Everybody will get an email. You'll have a link and an information in there. Get on. You'll take a short quiz. As long as you pass it, then you'll get your continuing education credits. So again, after the webinar, everything on that will get sent out to you. So today, for the purpose of learning objectives, we're going to teach you the basics of optical fiber and how it works. So, we'll explain what an optical fiber is, the purpose of each of its three components, the core, cladding, and the coating. We're going to talk about the meaning and importance of total internal reflection. We'll talk about the advantages of using fiber optics versus copper cable. We'll look at the meaning and importance of a few different concepts. Talk about Snell's law, index of refraction, angle of incidence. We'll also talk about the wavelength and frequency as they relate to a fiber and how they're used. And then we'll also talk about some attenuation and dispersion, get into the performance of the fiber itself. And then as we wrap up the end, talk about some newer, more advanced types of fiber that you can find out in the market. So the agenda for today, again, introduction, Tim Buffkin, went over the learning objectives. Next, we'll get into the presentation. And then at the end, we will do a Q&A with some of the time that we have left. We do ask that we keep it to technical questions regarding this presentation. If you have other questions, we're happy to help you out with, or if you have some business-related matter to discuss, obviously we'd prefer to take that offline. So with that said, let's get going. So fiber optics, right? We're essentially talking about the technology used to transmit information as pulses of light through thin strands of glass or plastic fibers over long distances, right? The light is going to constantly, basically bounce back and forth inside of the core against the cladding of the core as it travels down the fiber. So one thing we had or actually, no, I'll get into the second. So one of the big things that we're going to talk about with fiber is what's called total internal reflection, or as I'll just refer to as TIR. So TIR occurs in nature with light, electromagnetic waves, sound, and even water waves. But as we refer to it with light, TIR is going to occur when the light reaches the boundary of two mediums, as in, water and air, right? When it reaches the boundary of those two, or where those two mediums meet, and the angle it hits at, or as we will call it, the angle of incidence, is greater than the critical angle. And we'll get into more of that info on what those are. And then also, the light is going from a dense medium to a less dense medium. So, for example, right, water to air, water being the more dense medium, air is being the less dense medium. So, again, with TIR, that's going to happen when you're reaching the boundary of water and air. Then, when the water, again, we're going from less dense to more dense, and then the angle that the light hits that meeting point is greater than what we call the critical angle. Okay. Now, next I've got unfortunately, we're having some difficulties. I got a video that I was going to show that talks about a lot of the concepts that we're going to hit on this presentation. And it gives a really neat visual representation, a really neat experiment on how it works. Unfortunately, for some reason, I can hear the sound just fine on my computer, but we cannot get the sound to come through on the meeting. So instead of necessarily playing the whole video, I'm gonna click through just a couple different spots here, and then I'll kind of explain. He's got some captions that explains what's going on, but then I'll kind of talk over it as well. So we're gonna get this going. All right. So I'm going to go ahead and move ahead to his experiment. So in this experiment, what he's doing, so he's got a bucket that he modified with a screen, and the other side he's got a plug, basically a stopper. So he's going to pour this bottle of propylene into the bucket, and then he's going to set up a laser that's going to shoot through the propylene. And then what we're going to get on the other end of it is going to be a key example of some of the concepts that we're going to talk about here in a little bit. So he's going to turn on the laser, pull the plug out, and here you can actually see the laser following the liquid all the way down to the bucket, even though the laser is shooting straight across. This is total internal reflection. So there's the first reflection, second reflection. So that's what's making it go through. So in here he mentions, so we're going to talk about that's the density, that's of the two different mediums. So essentially what's happening is the light is going from the propylene to the air. So part of it is escaping, part of the light's escaping, part of the light's bouncing down. So that's what's creating this. So we're going to move ahead here just a little bit to the next part. And I'll have to apologize. Like I said, that some of this stuff, I'm going to have to just skip over because it's going to be hard to. So this part right here, we're going to go back to this later on when we talk about the signal that gets sent through, right? So fiber optics, what's getting sent through is basically pulses of light, right? So you have a code that's put together, and it's sent through as pulses of lights as 1 and 0s, right? Off and on. So that code is sent out by a transmitter, and then it's received by a receiver that knows how to identify that code, and then how to translate it into what's going on, right? Or what it's supposed to do, or what it's supposed to say. So it's that code that's going through the fiber optic cable. So then once we actually, I'm going to scoot this last little part. So here we're going to touch on attenuation here in a minute. That's basically the power of the signal going through. But so the last key part here, and again, I apologize for the technical difficulties. So you're actually looking at the laser beam going through. You can see how the angle is going to change as it goes through, but the light going through is actually going to spread out, right? So because the angle in which the laser is hitting is changing, we're losing light as we go through. All right. So again, right, kind of again, apologize for the technical difficulties on the sound here, but at least visually, you can see what's happening here with the laser as it bounces through that material. All right. So with that said, and again, some of these concepts I'm going to come back to and we'll explain a lot more in detail, but at least visually, you can see what was happening with the laser as it went through the propylene. So again, yeah, I mean, why use fiber optic cable? It requires a lot less space. A fiber optic cable with the same bandwidth capacity as a comparable copper cable, we're talking about less than 1% of both the size and the weight. So it's really just, honestly, it's way more efficient in how it operates. Two, you can go, because of that efficiency, you can go a lot farther than copper cables for a given bandwidth. And by bandwidth, we're talking about the amount of information that you can transmit at one time. So you look at the bar graph down here, and honestly, none of the copper cables are even showing up in terms of the distances that you can send a 1 gigabit per second amount of information through. The speed. A single mode fiber optic cables are just going to go a lot farther, and they're going to carry a lot more bandwidth, and which is why, obviously, the big thing now with fiber to the home and rural broadband, it's about getting rid of that copper that's in the ground and switching over to fiber. It just performs a lot better in every single way imaginable. And then another reason is that you don't get any interference. Fiber is immune to electromagnetic interference and radio frequency interference. So you don't get any crosstalk between fibers like you do with copper cables. Now, if you're not familiar with the crosstalk, basically what happens there is if you have multiple copper cables that are next to each other, and if you send a signal down one copper cable, that transmits that frequency or transmits that information outside of that copper cable, and you can actually interfere with the cable next to it. So that signal can jump to a different cable that's right next to it or potentially touching it. But with fiber, even if the fibers are touching each other, you're not going to get any kind of that crosstalk. You're not going to get that mix up of signals between different pieces of fiber like you would with copper. But then also too, fiber is more secure. It is more difficult to tap and be able to pull information out of. Whereas with copper, it's a lot more simple to break into a copper cable and be able to bleed data or bleed that signal out of that cable itself. So again, how does it work? So this picture right here is basically what we were looking at with that video, and with that laser going down that stream of propylene. So what you're going to have here is you're going to have the core of the fiber in yellow and then the cladding in the gray. The acceptance cone is basically, if you think of this fiber right here, the bottom left side of that fiber, that's the beginning of the fiber. The acceptance cone is where you're going to have equipment that's going to plug into that fiber, and then that's where the light is going to enter the fiber. So then from there, that air that's coming in from the acceptance cone, as it hits the cladding, you're going to have light that's going to hit that cladding, and it's going to refract out of the fiber, and that's light that you're going to lose. But then most of it is going to be refracted internally and continue down the line. So again, with the video, with that stream of the propylene, you saw that with that light going and being very strong at the very beginning, reflecting off the side, going to the other side, and then as it reflected, you lost a little bit more light each and every time that light bounced off where the propylene met the air. Okay. So the very heart of it, this is what the fiber does, what the light does inside. And again, refract is just a fancy word for meaning bent. So we're bending the light as it goes down the fiber. So the optical fiber is going to be composed of two layers with different indices of refraction. You're going to have the core that's going to have its index, its refractive index, and you're going to have the cladding, which is going to have its refractive index. So the index of refraction is basically a way of measuring the speed of light in a given material. So going back in the video, I stopped on it for just a second, but he talks about the indices of refraction, the propylene, and in the air. And the refractive index of the propylene, it was like 1.42, 1.43. The air was 1. Okay, so you had your two different indexes. And then obviously light travels fastest in a vacuum. So to kind of go into this a little bit more, so we'll look at what's called Snell's law. So Snell's law was discovered by a guy named Wilbrord Snell in 1621. So what we're actually doing is he looked at the relationship relating the index of refraction in a given medium and the incident light angle to the index of refraction in the new medium. So basically what he's doing here is while you have your indices of refraction in your two different mediums, Snell also took the angle to the index of refraction and incorporated that into how the light continues to go in between the two mediums. All right, so let's look at, take these three pictures on the right. So you have your two mediums, right? Your N1 and your N2. That's, the N1 is our core, our N2 is the cladding. So not only do we look at the index of refraction of those two materials, we're going to look at the angle. So in A, so what happens if the angle of incidence is less than the critical angle, all of your light is, in this case, is going to escape the core through the cladding. So in this case, you lose all your light and basically your signal is done. On B, where the angle of incidence is equal to the critical angle. Now, in theory, what's going to happen here, and let's assume, again, in theory, our piece of fiber is perfectly straight. What will happen when the angle of incidence is equal to the critical angle? The light will actually carry perfectly down right in between the core and the cladding all the way to the end of the fiber. However, real world, that fiber is never perfectly straight. So this realistically doesn't happen, but in theory, that is what would happen. And then on C, the last part is when the angle of incidence is greater than the critical angle, that's when you get refraction where the light bounces, through the cladding and comes back down into the core and then continues down its way. Right. So again, Snell's law is taking your index of refraction of the two different medians, but now incorporating the angle at which the light is entering the core and bouncing off the cladding. Everybody following me? Perfect. There is a test after this. Oh, let me get back. There we go. So with that said, using Snell's law, we can determine an angle that's really important. So if the light enters the fiber core at or below this angle, then it's going to be reflected down the core, and the light will continue to be reflected down the core. So that is, there will be total internal reflection. Okay, so on the picture here, you can see the angle at which you need to come in at, and that goes back to the cone of acceptance that we pictured on one of the earlier slides. So as long as that angle or that cone of acceptance is met, then you're going to have light that's going to continue to propagate down the fiber itself. And again, that's your acceptance angle, or the maximum angle at which a ray of light can enter the core and still go down the fiber itself, right? So obviously your acceptance angle, your fiber is round, so really it's a cone shaped, right? It's not just this two-dimensional angle that you can enter the fiber at. So there's going to be two more important concepts of optical fibers that we need to understand in terms of how it works. The first is going to be numerical aperture, and the second is going to be mode field diameter. Hope you guys are writing all this down, just so you know this will be available on our website, because I know there's a lot of terminology on here to go over. But first, let's look at numerical aperture. So again, the acceptance angle, which you immediately understood right off the bat. Okay, so recall that concept. Now you consider that laser needs to inject light into a fiber with that angle. So now you might think that the laser and fiber manufacturers would both find that angle useful and refer to that in their specs and refer to that routinely. Not the case at all. So instead, they use what's called numerical aperture, or NA. So NA is similar to acceptance angle in concept, right? So your working definition of numerical aperture is it is a dimensionless number that characterizes the light gathering capability of an optical fiber. Okay. So what that means is the higher the numerical aperture is, the larger the acceptance angle is. Therefore, you have an increased ability to gather or emit light. Okay, still following me? Perfect. So, why use NA and not acceptance angle? Well, two reasons. One, because in single mode fibers, you can't calculate the acceptance angle using just the indices of refraction for the core and the cladding, right? Those are the two numbers, the more dense and less dense numbers that we use to calculate that, right? To calculate the difference. But why? Well, that reason is because the light doesn't stay in the core alone. It actually penetrates just a little bit into the cladding. So if you think about bouncing a basketball out in the driveway, right? You throw the basketball down, it hits hard concrete, and it bounces right back up to you. Well, in this case, in the case of fiber, the light doesn't hit that meeting point between the core and the cladding and just bounce off it. It actually goes up into the cladding just a little bit, bends the light, and then comes back down. So consequently, the energy of light is just spread out over an area that's greater than just that of the core. And that we call the mode field. And we'll discuss that here in a couple slides as well. The second reason of why we use NA, that's just what the fiber manufacturers use. So honestly, that's just what we go with. So just to kind of give you an idea, looking at this is from Corning's data sheet on their SMF28 Ultra fiber, they actually list out the numerical aperture. Okay, so it says on here, NA is measured at the 1% power level of a one-dimensional far field scan at 1310 nanometers. Okay, so that's your wavelengths. We'll talk about wavelengths in a little bit. So you're not going to find acceptance angle on here, just that NA, the numerical aperture. So again, to go back and touch on the mode field. So remember, if the light is going just outside of the core into the cladding, and if you were, essentially, if you're able to zoom in far enough, you would see what you have on the right here, where the light hits where the core and the cladding meet, bends up into the cladding just a little bit. And you see the light just bend right back around, and again then goes back into the core. Because again, it's not really reflecting reflecting or bouncing off that. It's bending through the core, and then that's what's sending it back down. And again, going back to why NA is used versus just the angle, or just the incidence of the median. So again, with the mode field diameter, we're actually going to look at the diameter of the core, and then we're going to add that little extra bit of cladding. So the mode field diameter is going to be the full width of area in which the light energy is distributed, and that gets measured, like especially like fibers in general do, it gets measured in microns. So if we go back to Corning's data sheet on this with the SMF28 Ultra, it will show you the mode field diameter at different wavelengths. And again, it's important to notice that it does change depending on the wavelength itself. So at a 1310 wavelength, the mode field diameter is smaller than it is at a 1550 wavelength. So in the case of a 1310 nanometer, the mode field diameter is 9.2 microns, plus or minus 0.4. 1550, we're at 10.4 microns, plus or minus 0.5. So now we go in, we've got different types of fiber that have been used over the years, starting with, essentially just from a physical standpoint, your larger fiber core, which is our multi-mode fiber, start out with an OM1 fiber that had a core of 62.5 microns. Now your cladding and your coating that's added on, right? The cladding is still you're still looking at the same diameter overall of the fiber. So your cladding diameter is 125 microns in all your modes of fiber here. And then your coating, which protects the glass inside, right? That protects your cladding and your core. Then as we moved up to OM2, OM3, and OM4 fibers, we decreased the diameter of the core down to 50 micron. And then as technology advanced, we were able to make more efficient fiber that brought on these single mode fiber. Now that you can see, you have a core diameter of only 8 microns. So what we could do in multi-mode fiber, because the fiber was so wide, we could send different wavelengths down that fiber at the exact same time. With single mode, you're just sending the one wavelength. So you're just sending that one signal down, that one wavelength. Now, the plus side of the single mode, though, is when we go back to the cone of acceptance, right? The angle at which you could send the fiber into, with the core being that large, those angles can increase a lot more. To whereas you go into that tiny 8 micron core of a single mode fiber, you think of the difference in a core being this small versus this big, right? The light has to get shot through that single mode fiber at a much flatter angle than you could the multi-mode fiber. Okay, so because of that and because of the angle that we're actually going into the fiber with, that increases our information carrying capacity, but also increases how far that signal can go. And again, we're going to go back and look at the wavelengths. And so a lot of this has to do with the wavelengths that we're sending through. With multi-mode fiber, we're going to have shorter wavelengths or lower, we're gonna have shorter operating wavelengths. So starting at 850 nanometers with a shortwave multimode, and going up to 1300 for long wave multimode. Then once you hit about 1310 nanometers, that's when we get into single mode. And 1310 is going to be where a lot of your standard networking, standard network, your fiber network are going to operate at the 1310 wavelength. 1550 is a long wave single mode. That's also going to be one of your more common types. But obviously you can continue going up to 1625 nanometer. And that's when you'll typically, you're going to start getting into more of the WDM or DWDM. And I'll touch on what that is later on the slide when we talk about some of the newer fiber types that are out there. So, the properties of electromagnetic signal. Again, we talked about the wavelength, right? So this is the distance between identical points on a wave, and that's going to get expressed in nanometers. So in the example of A, that's going to be more of your lower frequency, right? That's your multi-mode wavelength right there. So longer length in between the individual waves and less waves overall. Then obviously as you increase the frequency, right, you're increasing the data, you're increasing the input and the output. So you're shortening that distance in between the different waves. So now when we look at the fiber performance factors, there's really two key optical fiber performance factors that we're going to look at that we can discern and basically figure out how well a certain fiber can or cannot perform. The first one is going to be attenuation, and that's going to look at the loss of the signal strength. So that we're going to express in decibels of power lost, or usually people just refer to as a dB, right? Decibel dB. We have two different types of attenuation we'll look at: intrinsic attenuation and extrinsic attenuation. This is going to impact the ability of the receiver, or the ability to get the signal to reach the receiver with a sufficient amount of power. Again, going back to the video, as that laser went down the stream of liquid, you saw the light become less and less bright over time. So kind of think of it, that's your attenuation, right? The light is getting weaker as it goes down, the fiber. A 3 dB loss in power is going to equate to a 50% loss from what you started with. So we'll get into some of the more finer details on what a typical loss may look like, but that's an important thing to keep in mind. The next, we're going to look at dispersion, and this can be the spreading of signal pulses. So just to go back really quick to this slide, here's our signal pulses. So dispersion is going to be spreading these wavelengths, like spreading the individual wave out. So that's going to include modal dispersion, chromatic dispersion, polarization mode dispersion. All right. So again, a lot of words to keep up with, but we'll hit on each one of these individually. But that's going to impact the ability to distinguish the signal pulses. So attenuation is about power. Dispersion is going to be about receiving the information correctly. So again, with attenuation, loss of signal strength, this is going to be the most important fiber performance specification for a user. This is going to be, if somebody is building a fiber network, whether it's fiber to the home, long haul, this is going to be the number one thing that's going to get looked at on a spec sheet is what is my loss of power over distance. And again, this is going to be found on a spec sheet. So in the case of Corning's SMF28 Ultra, right? If we look down on the bottom right, if you have here per different wavelength, so at a 1310 nanometer wavelength, you're going to have a maximum value of a 0.32 decibel per kilometer loss. So for every kilometer you send a signal down, you're going to lose no greater than 0.32 dBs. But just like with going back and looking at the mode, and our mode diameter, this is going to change depending on the wavelength as well. So at a 1550 wavelength, instead of a 0.32, we're only at a 0.18. So that means at a higher wavelength, we're going to lose less dBs over the course of that kilometer. So again, all this is going to allow somebody to do is when they're planning out their fiber network, saying, okay, I need to make a run from point A to point B, and there's 10 kilometers in between the transmitter and the receiver. They can go in, use this number, and say, okay, I will have no less than, in this case, 10 kilometers. At 1550, I will have no less than 1.8 dBs lost from point A to point B. The other thing that can add loss from point A to point B is connecting fibers. So again, maybe instead of, at 10 kilometers, maybe you've got 100 kilometers, right? So now between there, you're going to have places where you have to connect multiple fibers together, and you might do a fusion splice. You might add in connectors. You might be building a fiber to the home network where you're using optical splitters. Each one of those things is going to add a dB loss to that run from point A to point B. Fusion splicing is going to be the most efficient way to connect fibers. The technology with fusion splicers has gotten so much better over the last 20, 30 years that they're way easier to operate. And the loss is almost zero with the fusion splice. I mean, you're really, 0.05 dBs or lower is where you're going to be with a fusion splice. Now, mechanical connectors are definitely widely used because they're very convenient. They give a lot of flexibility. If you're in an area where you're connecting customers, disconnecting customers, you can go in and, disconnect a connector, plug one in somewhere else. So again, it offers a lot of flexibility, but the dB loss is a lot higher, typically anywhere from 0.2 all the way up to a full dB. So remember, going back to our 50% loss off of 3 dBs, if you have 3 connectors in between point A to point B, you've lost 50% of your power. All right. And then lastly, for a fiber to the home build, we have optical splitters where we're going to take one fiber coming in and you're going to have 2 fibers leaving, or 16, 32, 64, even up to 128. So obviously when you're splitting the fibers that way, you're also splitting the light. So it's no surprise that you're going to lose a lot of power in those fibers that are leaving the splitter, right? Because again, you're coming in with one. If you're leaving with 32, you're splitting that light 32 ways. So in the case of a 1x32 splitter, we're losing 18 dBs of power in those outputs. But again, it's not surprising given what you're doing. But typically, though, especially in a fiber to the home build, when you're using the splitters, those splitters are usually in a location to where from the splitter to wherever you're going to, a business, a home, whatever it is, you're usually not traveling super far. So at that point, you're still going to get to where you're going to with the proper amount of power. And so again, let's kind of show you basically your optical loss of power. So again, for every 3 dB loss of optical power, you lose 50% of what you had before, aka the divorce law. But so sorry. So when we look at intrinsic attenuation, loss of signal strength, again, this is going to be caused by substances within the optical fiber, right? The design of the fiber, right? Multi-mode to single mode. You can see on the chart on the right, your attenuation goes up a lot higher with multi-mode, because again, that goes back to a lot of just the size of the fiber core, right? So those are things that are going to affect that. But then again, as you move towards the right in single mode, that attenuation goes down a lot more. And then we'll talk about some of these absorption and Rayleigh scattering phenomenon as well. We'll hit on that here in a little bit. So intrinsic attenuation. This attenuation is internal to the fiber itself. It can't be affected by outside influences, right? So this is going to be done this is going to be from the manufacturing of the fiber itself, not something that's going to come from the cabling. So two main things we have here is absorption, where that's a photon will give up kinetic energy when it interacts with an electron and excites it to a higher energy level. Basically, it's absorbing the power as it goes. Now, the Rayleigh scattering is going to be what happens when light is scattered as the result of defects in the glass. So these imperfections are microscopic and are going to happen during production. Basically think of this as a flashlight or even a laser hitting a disco ball, right? It hits that little imperfection in the glass, and then all of a sudden the light spreads out everywhere. Just like hitting a disco ball spinning around a room. So those are two for intrinsic attenuation. Now, when we go to extrinsic attenuation, now we're talking about something that happens outside of the manufacturing of the glass itself. The most common that we're going to see is called a macro bend. So this is going to be caused by a large-scale bend of the fiber, which is visible to the human eye. You'll be able to see it, and that makes the fiber is going to be bent at less than the safe minimum bending radius. Okay, now the loss here is generally reversible once the bend is moved, but as you can see from the diagram, if you bend that fiber tight enough, you're going to increase the angle at which the light is hitting the cladding, and then you're going to get where the light now can no longer continue to refract and bend back into the core, and it's going to escape through the cladding. Now, you could bend it to a point to where it just stops light from going through, but typically what you're going to see is just a loss of light or a loss of dB that's going to be significantly greater than what you would expect. But again, it's reversible. Usually something like this, it's usually going to happen in a splice tray. Maybe you have a splicer at the end of the day on Friday. He's trying to get home as quickly as possible, miscalculates the length of the fiber that he has, and didn't line up in the tray. So he just kind of shoves everything in the tray so he can get it closed up and go. That creates the bend. To fix it, all you have to do is go in there and you can just basically reroute it, right? But you're going to take that bend out, and then everything goes back to normal. So it's going to operate just like it did before. So again, that's going to be the most common form of extrinsic attenuation that you'll see. Extrinsic, excuse me. The other is called a micro bend. So whereas the macro bend, you could see it physically, this is going to be a very small scale distortion in the geometry of the core itself. So just looking at the picture, you can see where in this case, the core is almost like it's been pinched in, or excuse me, the cladding has been pinched in, and that's causing the cladding to pinch into the core. Now we don't have a nice smooth surface or a route for that light to follow. Same thing. Now you have more dB losses. Now this can be caused during the manufacturing process, or it could also be caused by crossovers in a tube, where basically if you have fibers that are crossed over each other, and then you put a force on there and it, essentially kind of pinch each other, that can create something like this as well. It can be reversible unless the core has been permanently deformed. I'd say usually in a lot of cases, if you have a micro bend, you'll shoot it with an OTDR. You'll see where the issue is in your fiber, and then typically you're just going to go in, probably cut out the bad part of the fiber, and then just resplice everything back together. So next, we're going to talk about dispersion. So dispersion is going to be the spreading out of a light pulse as it travels through the fiber. Okay, so again, this is going to go back to the wavelengths and the signal that's actually getting sent through. So we're going to have three types of dispersion that we'll talk about: chromatic dispersion, modal dispersion, and polarization mode dispersion, or PMD. Chromatic dispersion. So chromatic dispersion is the phenomenon of pulses spreading due to the different colors of light or wavelengths traveling at slightly different speeds through the fiber. Okay, so what happens in this case is, as the pulse travels down a fiber, right, the dispersion is going to cause the pulse to spread out. So if we just, even looking at this graph on this picture on the bottom left, your signal at the input is nice and high and it's not that wide, but at the output, you can see that the signal is a bit lower and wider. But what can happen though is, going over the bottom right, we have our, again, 1 and 0, right? Our 1 0 1 0. That's what our signal is. If you have the signal spread out to where now maybe the signals are overlapping, that can cause bitrate data on the receiver side. So again, we have the power going from point A to point B, but because of this chromatic dispersion and how this light is traveling down, it overlaps, and again, that's going to create difficulty on the receiver side trying to decipher what the information actually is. So then you also have modal or intermodal dispersion in multimode fiber. So now this can be the spreading of signal pulses as they travel down the fiber as well. But now in this case with multimode fiber, because again, you can send multiple wavelengths down the multimode fiber at the same time, right? So these are going to travel, essentially at different speeds. But what can happen is, let's say you're sending three different signals down a multimode fiber, right? So your input is a code that reads AAA. Your next one is a code that reads BBB. The next one is a code that reads CCC. Okay. But with modal dispersion, what could happen is, because all of these are traveling down the fiber at different times, but eventually they could overlap to where instead of the other end getting AAA, BBB, CCC, and getting the signals in that order, you might get AB, AC, BA, CBA, right? Something to where now it is really jumbled because it's overlapping in the multimode fiber. And then lastly, we're going to talk about polarization mode dispersion, PMD. So single mode optical fiber is going to consist of one propagation mode, which in turn is comprised of two orthogonal polarization modes. So asymmetrical differences in the fiber itself can introduce a really small refractive index variation between the two modes. So this is what's called a birefringence. So, when we looked at all these, the wavelengths and the light reflecting off of, between the core and the cladding and a fiber, all these pictures are two-dimensional, right? So the light's just doing this. But in reality, in a fiber, if you think of, the light's coming towards, my camera on my computer, instead of just going up and down, it's going here, 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 right? So it's 360. But what can happen though is if the core isn't perfectly symmetrical, it can then create issues with the angle in which it's reflecting or bending, refracting between the core and the cladding. So, and if you look on the bottom left, you'll see the polarization mode dispersion. You can see how basically what can happen is it can throw off how the signal is traveling down. And then even if we go to the bottom right, you have your input signal, but then if your input signal should be like what's on top, right, to where it's regularly spreading out, the the core not being perfectly symmetrical can create almost can create the different angles, and that's going to mess with the signal again, which is going to mess with the receiver and how it interprets the data being sent down. So this is going to be cause multiple different things. It could be the manufacturing process of the glass itself. It could be internal stress caused from the cabling process, could be external stress. But this is something, obviously, the more data you're trying to pump through becomes critical as the transmission speeds increase and the distances increase. So again, kind of to recap this all, this all we're talking about leading to bit error, or again, getting the signal cleaning, or getting the signal from point A to point B as cleanly as possible. So our theoretical input of, again, ones and zeros, right, is on, off, on, off, on, off, on, off, right? So very clean 1 0 1 0 1 0. The actual input, which is going to be our wavelength, is going to look like the second from the top. That's going to be the actual input going through the fiber. Now, again, we are going to have pulse broadening. That's going to happen, but you have a range of in which it's still acceptable. So for now, if we go down to the third line, you can see, obviously, the pulses have spread out, but you still have a distinguishable 0 1 0 1 0 1 0 1 0, right? We still have separation between the pulses. But now go down to the bottom. If you have too much pulse broadening, right, now we're going to run into issues because we don't actually have separation of the pulses. And again, that's what's going to lead to the bit error. Because again, we've got enough power to get to the receiver, but now the receiver is going to see this, and it's not going to know where the zeros are, essentially. So again, now the data isn't coming through as clearly as it needs to be. So kind of to recap, you have the attenuation, which is, again, loss of signal strength. Very much affected by the cable manufacturing process. Again, we can't get any better, or we can't get any lower attenuation than what we're given by the fiber manufacturer. So if, in case of it, we'll take Corning. Corning says at 1310, it's going to be no greater than 0.32 dBs per kilometer. That fiber will never have any better attenuation than that. So anything else that happens, whether it's in the manufacturing process, manufacturing process or external factors, you're never going to get any better than that number. So your typical maximum individual and 5 final cabled values for single mode fiber is, again, 1310 and 1550. That's your maximum is going to be 0.35 and 0.25. Now, you will recall, obviously, that the Corning, the SMF Ultra, is 0.32. I think it was 0.18 at 1310 and 1550. So theirs are better than the typical single mode fiber. Best practice, you want to be, really no greater than 0.34 and 0.2. But again, obviously, the Ultra performs better than that. Now, with multi-mode fiber, your typical attenuations are at 850 and 1300, you're 3.5 and 1.5 dBs per kilometer. So again, a huge difference in our attenuation between multi-mode and single mode fiber. So at 850 nanometers, we're losing half of our power after 1 kilometer. So easy to see why single mode fiber has kind of become the standard. Best practice, honestly, it's one of those things. I'm not really sure necessarily what would be considered the best practice. If there's anybody watching that deals a lot with multi-mode, I'm not really sure necessarily what that would be considered. But again, from what we tend to see, at least on the multi-mode fibers that we work with, 3.5 and 1.5 dBs per kilometer seems to be, about what the normal is. And then dispersion, again, right? We're spreading of the signal pulses overwhelmingly from the fiber manufacturing process. excuse me, this is going to be specified by the fiber supplier. So again, just like the attenuation having numbers associated with that, this is going to be information that's provided by the fiber supplier. Therefore, it's really not going to be affected by the cable design or the cable manufacturing process. It really just kind of it is what it is in a finished cable. I guess unless the cable is just very poorly made, in which case you're probably going to have a lot of other problems, I'd say, within that cable. And then the finished cable limits are just not used. So, taking all that info, there are some newer advanced fiber types. So, we talked a lot about the SMF-20 Ultra, its attenuation and its performance, but increases in bandwidth demand and transmission distances have led to some newer special types of single mode fiber. Again, the types like your Ultra, SMF-20 Ultra, those are, I would say those are used in 95% of the cases. But you do have what's called a non-zero dispersion shifted, or NZDS, single mode fiber. And again, right, you recall us talking about the chromatic dispersion. So with this fiber, you can actually correct for dispersion, basically kind of like how eyeglasses can, right? It can help refocus that light and help keep that dispersion from happening. The two best known types of NZDF single mode fibers right now in the market is going to be the Corning Leaf and the OFS True Wave. This is going to be, the standard is going to be G655. Now, this cable, though, is really designed for use with dense wavelength division multiplexing, or DWDM. So I mentioned this earlier on. So this helps boost bandwidth. So now your DWDM is going to be networking equipment. So this isn't going to be passive optical gear. This is going to be active networking gear. But what DWDM is going to do is it's essentially going to, calling and for layman terms, it's going to help you utilize a single mode fiber like you would a multi-mode fiber, by the way that you're going to be able to send multiple wavelengths down the exact same fiber. But what this is going to allow us to do is fit way more bandwidth into a single fiber, and essentially almost making a single fiber act like it's multiple fibers in one cable. So when we compare a standard single mode fiber, you're looking 10, 40 gigs per second worth of bandwidth. And that number is continuing to climb as new technology comes out. But with the NCDS single mode fiber, you're talking 100 gigabits plus of bandwidth. So yeah, obviously a lot more bandwidth than that. So really cool what they're able to do there. Also, you can get a lot further of a distance out of that bandwidth. Standard single mode fiber, we're 60 to 90 miles before we have to re-up that signal. Whereas the NZDS, we're going up to 250. So this type of fiber, you're probably not going to see it, in your standard fiber to the home build, your standard fiber network kind of a thing. But you could see it maybe in a long haul fiber route where, let's say you need to run fiber from Atlanta to Grapevine, Texas. There you might use something like this, because now instead of having to have a comms hut every 60 to 90 miles and to re-up that signal, now you can potentially go up to 250 miles. So that's where something like that is going to come in. But again, still a majority of what most people are going to use a network for, something like the SMF-20 Ultra, is going to be the much more common type. Then to take it one step further, we can go to what's called a cutoff shifted single mode fiber, or G654 single mode fiber. And this essentially is going to be an ultra low loss type fiber. This was originally used for transoceanic submarine cables, which obviously you can imagine for that, you want to be able to get as much data as far as possible before having to, re-up that signal. So, right now, you're looking anywhere from 400 gigabits per second to a terabit of bandwidth per second, which is astronomical. So obviously way more bandwidth out of this fiber. and you can go distances up to 560 miles. So I mean, you're really getting a lot out of this type of a fiber. But the thing is, it really is optimized for uses between your 1550 and 1625 nanometer wavelengths. And just for example, look at your typical attenuation limits. 1550 nanometers were 0.17 dBs per kilometer. 1625 0.19 dBs per kilometer. So really efficient fiber. Honestly, I haven't necessarily come across many projects that need something like this. But again, right, your standard network fiber to the home, it's going to be very unlikely you would need this type of fiber. So in closing, just for fun, yeah, looking at the size of a fiber, I think it's pretty amazing. Obviously, I've been in the industry for a long time. I'm always amazed looking at a bare, a bare optical fiber, and thinking about the technology that goes into it and how it's able to get us what it does through the internet, right? You guys are able to watch me, and I'm able to share all this information on something that's barely larger than the size of a human hair. So pretty remarkable stuff. That's gonna wrap it up for me. I hope you guys enjoyed the presentation. Hope you learned a thing or two. I know we had a lot of acronyms and new words and a lot of concepts in here. And so I know I learned quite a good bit about fiber myself trying to get ready for this presentation. So yeah, again, I appreciate everybody's time today, especially those of you on the East Coast. Taking some time out of your lunch break. One thing to note in the chat, marketing put the link to the YouTube video that I was not able to get the sound on. It's like 5 minutes long. I definitely recommend watching it. Honestly, just the experiment part of it is really neat. So yeah, if you get some time, feel free to check that out. But yeah, I guess that's that. If there's any questions, I'll open the floor up to you guys. I'm sure everybody retained every single piece of that presentation right off the bat as well, because I know I did. I appreciate it, Dan. Yeah, so we'll have you can email marketing at incabamerica.com, and we can certainly send you the PDF of the presentation. But this will also be available online. So if you go to our website and you go to the Learning Hub, listen on our website, you can go there, you'll be able to find this presentation, and you'll be able to find all of the other presentations that we've done from ADSS engineering, OPGW engineering. I've done a couple fiber to the home presentations as well. So yes, this will be available on there. So there are devices which switch from different wavelengths, like step up, step down. Um, so that would be that's a really good question. I would have to think it's really at that point it would just be the networking gear. So again, right, kind of taking the point A to point B approach. You hit you hit 50 miles and you hit a communications hut. If you had a need to switch wavelengths, then that would basically just be your networking equipment that you would buy. So you would receive it at a 1310, and then like I said, depending on what you're trying to send it out. So yeah, absolutely, I'd be certain that any of the large networking companies would have equipment out there that would allow you to switch. So if you wanted to, and honestly, probably if you take the long haul route, for example, if you're wanting to go to 1550 wavelength, and then the data gets to a comms hut, and then from there you're going to go to a fiber to the home type of a build, you'll switch to 1310, then yeah, I'm sure without a doubt there's equipment that could do that. Yeah, not a problem. You have to see, I'm not as big on the active networking side of it. I know enough just to be slightly dangerous in it, but the blinking lights, as I call them, I'm not as fully up to speed to that technology. But I could say just from my experience that something like that absolutely is available. Yeah, no, appreciate you. Like I say, I've still got a couple minutes left. If anybody has any questions, also, yeah, feel free to email if you think of a question later on. Feel free to reach out directly. My email is tim.buffkin@incapamerica.com. So again, yeah, feel free to reach out and happy to help any way I can. All right. Well, I guess we're good. Hey, thanks a lot again, everybody. Thanks for taking some time out of your day and hanging out with us and learning a little bit about optical fibers. Appreciate it. Have a good day. And happy Thanksgiving to everybody next week.